Hello. So I think folks are still coming, especially in the classroom, but I think it's time to get started. So let's get started. So in the last week, I was talking about this SIMD programming, and especially this sort of somewhat lower level SIMD programming. So you manually vectorize the loops, especially when vectorizing, so compilers fail to vectorize certain loop. You need to do it somewhat manually. And an important case in which compilers somehow tend to fail very easily is loops with branches inside. So branches, I mean, if statement, right? So for that, actually, it's not that CPU is not able to vectorize this kind of iterations at all. So there are something called a predicated instructions. So you have a SIMD instruction, but only some of the specified lanes get executed. So other lanes are sort of intact. So this way you can execute certain instructions that appear in, for example, then branches of the if statement or else branches, right? So this is the machinery the CPU has. And okay, so here's the template for vectorizing loops if the loop contains branches. So let's say, so an iteration does something like this. So what you need to do is, so remember, so it's always that, so what you want to do is to execute consecutive iterations at the same time using a SIMD. So the main issue is that, so if you evaluate this expression, conditional expression for if statement for consecutive lanes. So some of the lanes are evaluated to true and others are evaluated to false, right? So you cannot simply execute this then branch for all the lanes. So this is why vectorization is challenging in the first place. So here comes the predicated instruction. So first you need to generate something called a mask. So it's essentially a bit vector of L bits. So each bit indicating a particular length should execute then branch or else branch. And in general, if it happens that all lanes evaluated to false or all lanes evaluated to true, then you don't have to execute both. But in general, you need to do both, right? So if there's any lane that evaluates to true, then you need to execute this TI, but it should be predicated on K. So you should execute this only on lanes whose corresponding bit becomes true, right? And you do similarly for S branch. So this is a typical template. So let me give you a, so there's some, something else you need to have in mind is, okay, so there's some values that you need to use after this if statement. Then, yeah, the SIMD value or the vectorized value for that particular value needs to be generated, right? So in which case you need to somehow mix values you obtained in the then branch and the values you obtained in the else branch. So for which you need some ways to blend two vector values, right? So this is what this blend instruction is for. So it takes a mask specifying, so it takes a mask and two vector values, and each bit of the mask specifies from which SIMD values the value needs to be taken. So it's essentially doing something like this on each lane. So if the corresponding bit is 1, then it takes a value from maybe I'm wrong. This may be B. So this is the value taken for unset bits, and this is the value for this is the value taken for set bits. Probably, I think that is the case. So this slide is wrong. So you can check it later. And actually, many predicate instructions have already similar functions, functionalities as a part of its instruction. So for example, this is a predicated add instruction, which basically adds two vectors A and B. So if it is not predicated, it's a simple vectorized add instruction. But it takes a mask and another vector specifying the value for lanes on which K is not set. So it's essentially computes A plus B and blends A plus B and C based on this mask. So again, I think I made a mistake, right? So it should be K C A plus B. So the last argument is the value for set bits. Okay. So here's a specific example. So for example, let's say you want to vectorize this kind of loop. And yeah, so each iteration executes either xi plus 1 or xi multiplied by 2, depending on whether I is odd, even or odd. So in terms of the pseudocode, you first generate a mask or some L bit mask, right? So each bit specifies whether a particular I is odd or even. So in this particular case, the mask will be 0, 1, 0, 1, 0, 1, 0, 1, right? And this is essentially the then branch. So you actually execute this plus 1 on all lanes anyways. So some of the values are simply wasted and discarded. So after you execute the then branch, you execute the else branch, which is this, and blend the values you obtained in the then branch and else branch using this mask, right? Again, I may be wrong. So I put these two arguments in the other way. But this is basically how you vectorize loops containing if statement. So let's translate it into the actual code, which is kind of ugly. So compared to simple arithmetic expressions, the compiler nicely supports. So first of all, you don't have a you don't have a nice ordinary looking expression for comparison. So you want to do this comparison on all the lanes, but you don't have anything like that somehow. So there is no reason why compilers cannot support this kind of expression, but somehow it's missing. So you resort to calling intrinsics. So something called compare instruction. It basically compares these two arguments and say you want to compare by equal. So essentially you're comparing this vector and z. So z, by the way, is just a 0. And it comes from and this is 0, right? So the other thing you have to do is to generate a vector of this one. So I mod 2, I plus 1 mod 2, I plus 2 mod 2, right? So for that, you first generate a vector of I plus 1, I plus 2, I plus 3, until I plus L minus 1. So there's no convenient intrinsics for that. So we need to roll your own. So let's call it a linear, but writing it by yourself, it's not that difficult. And you take bitwise AND with this one. So fortunately, this bitwise AND is supported as a nice expression by the compiler. So this is actually the bitwise vectorized AND operation. So bitwise AND operation. And this is essentially the what you need to do on in the then branch, and this is what you have to do in the else branch. So the I'm sorry, or it should be I'm sorry, it should be vxi multiplied by 2, and so you give a mask. Right, so if the mask is the mask bit is set, you take, well, I may be somehow screwed up, but it's basically you are simply blending values from T, the value you obtain for then branch, and the value you obtain for else branch by using mask. So again, I may have made some mistakes in details, but this is how you basically do for so manually vectorizing loops containing if branch. So the other situation in which compilers tend to fail to vectorize, again without fundamental reason. So there's no fundamental reason why compilers cannot do that, but well, as far as we can tell, the many compilers simply fail to vectorize is loops containing non-contiguous memory access. So what I mean by so loops containing non-contiguous memory access are basically loops, for example, accessing arrays, but the index you are using to access arrays is not contiguous. I mean, for consecutive iterations, I plus 1, I plus 2, I plus 3, consecutive iterations access non-consecutive elements. This cannot be simply done by a vectorized load instruction. But again, it's not that CPU doesn't have an instruction doing something like this at all. So there's something called the gather instruction. So gather instruction is basically an instruction that takes a vector of indices. So I0, I1, I2 until L minus 1. So again, L is the number of lengths. And you get the gather instruction takes another base pointer, and you access these L elements with a single instruction. So more specifically, this is what the actual instruction or the intrinsic function looks like. So this is a 512-bit version of gather instruction. So I32 indicates that each index is 32-bit. So this is a vector of indices. Right? So it's 512 bits. So 32-bit, 16 32-bit indices. And you get a base pointer, and you get a scale element. So it accesses these locations. So you take the ith element in this index vector, scale it by multiplying it by s. So the s typically is a stripe. So the size of a single element, for example. And access it as if it is a pointer to a float, so single precision floating point number. So this is what this gather instruction does. And there are some other similar versions, for example. So whose difference is the size of each index and the type of the element you get as a value. For example, this MM512 I64 gather PD takes 8 64-bit indexes and get 8 double precision PD, 8 double precision 64-bit values as a return line. So something like that. There's some other similar versions. So this way you can vectorize essentially any any sort of loop. So no matter how the loop accesses memory, so using pointers or arrays or whatever. And the opposite is scatter instruction. This is a store, essentially the vectorized store instruction. So it takes, again, a vector of indices and a base pointer A, and a vector of values that you want to write to. So this is, exactly the opposite of gather instruction. And similarly, you have many variations like this. And both gather and scatters have predicated versions. So it can be used for example, loops in the containing the if statement, and you can use these predicated instructions inside a then branch or else branch of if statement. So instruction sets are pretty actually very general. And the other situation you often encounter when you are vectorizing using only a high-level method and compilers fail to vectorize is loops having another loop inside. So this is usually called something like outer loop vectorization. So a typical situation is like this. So you have an outer loop and you have an inner loop, and you want to vectorize this outer loop. So you want to execute I plus 1, I plus 2 until I plus L minus 1 of this outer loop. So this is actually a situation in which a compiler somehow often fail to vectorize. Well, actually, depending on what this inner loop actually does, whether the complexity of vectorizing this loop is very different. So in the very simple case, this limit does not depend on I. So no matter in which outer loop iteration you are in, this inner loop executes the same number of times. If this is true, actually the vectorizing this outer loop is not that complicated. So you can do it very easily by yourself. But somehow, in my experiences, compilers still fail to vectorize this kind of code. So I think it's very useful to be able to manually vectorize this outer loop by yourself. Well, especially when this limit is loop invariant. So it doesn't depend on I. Well, in that case, you simply execute this for loop. And each time you execute this body, you simply execute consecutive iteration using simple instructions. Okay, so this is what I say. So that the trip count of the inner loop is the same across all the lengths. I mean, it doesn't depend on this I. Then, well, there's no particular difficulty in executing this entire loop in the vectorized fashion. So the more general and the more difficult cases when this inner loop has different trip counts depending on I. So for example, for I equals 0, this limit is somehow 3. And for I equals 1, this limit is somehow 5. Then you need to have a vectorized code in which this particular length execute only 3 times, and the next length execute 5 times. So you need to be able to write a code that does something like that. But again, there's a template you can actually master. So for the sake of generality, let's assume that the inner loop is actually a while loop that repeats as long as the CI holds. And when this CI becomes false, depends on I. So this is the situation we have to deal with, right? Again, the predicated instructions are very helpful. So the entire loop continues as long as there's any length among the lengths. So there's any length on which this condition is true, right? So that the entire loop continues as long as there's any bit set in this C from I plus I plus L. Sorry, so from I to I plus L. And you execute this BI to I plus L, but it should be predicated on C. So this is the template you want to master. And again, so you need to translate it into typically lots of intrinsics, and the code becomes very ugly. So here's just a summary. So the vectorization is basically all about translating this loop into something like this. The loop counter advances L at a time, but a single iteration executes L consecutive iterations at the same time. So you simply look into every one of these statements and expressions inside and convert every expression into its vectorized versions. So whenever you have, for example, an expression X, then you think about, okay, so how you can generate this X for consecutive iterations from I to I plus L. So you simply translate every single statement and the expressions in this way. And vector extension supported by the compiler is very helpful for arithmetic and bitwise operations. You can use pretty much the same expression that you use for ordinary scalar values. But for other cases like comparison, you need to resort to intrinsics, and the code becomes ugly. And I forgot to mention, well, so if you actually are very familiar with a C++, you can make these ugly expressions much nicer using something called operator overloading. This is what I gave to you in the Jupyter notebook. Okay, so if there's any question at this point, I guess let's have some time to work on this low-level SIMD programming on this. I'm sorry. So the Jupyter notebook, the name of the Jupyter notebook is PD06 SIMD Vext. So this is about explicitly manually vectorizing arbitrary piece of code. So, well, in the last week, you had some time to play with this high-level SIMD programming, and the idea was just to play with the compiler and see how likely that the compilers are able to vectorize a certain loop. But the basic thing I want you guys to take away is what compilers often fail to do so. So the PD05 notebook is about how capable typical compilers are. And the idea was to share the results using Excel notebook. And I took a look at some of the Excel sheet, and so there's some of you who have contributed to much to the collaboration, and I thank those of you who did that. So depending on where you are, you can still play with this PD05 or jump into PD06. Well, it's not that you need to finish PD05. So if you think you are at least mentally ready for working on this explicit manual vectorization using vector extension and intrinsics, then I recommend you guys to jump into this PD06. So let's have some time to do this. Let's say until for 20 minutes, so until 5:40. Okay. So, so let's start talking again. So I don't expect you guys to finish this PD06 in just a matter of 20 minutes. So I guess you need to allocate some of your time to finish this one. But so the first problem you asked to solve is this vectorized version of this integral. So this is the piece of code you have already dealt with when you master the multi-core programming, right? So in this program, you do the same thing, but with SIMD instructions this time. And the main challenge you wanna address here is, so how you can deal with this if statement. So because the function you are integrating is something like this. So depending on whether this 1 minus x square minus y square is positive or not, you need to do different things, right? And basically you wanna execute. So let's say you wanna vectorize this inner loop, then you want to execute L consecutive iterations of this inner loop using SIMD instruction, right? And then the main challenge here is that okay, so how you do this, right? And basically you want to have a vectorized compare instruction that generates a mask and the predicated execution on this square root expression. Or you can simply zero the zero of this z on lanes on lanes whose original value was negative, right? So it's not necessary that you need to do a predicated square root instruction. You can just change the negative values to 0 before taking the square root. So the thing you want to become familiar with is how to search necessary intrinsics, for which there's already a pointer from within the slide, but you wanna become familiar with this intrinsic slide. So you can find necessary functions from this side. For example, so you have some gut feeling that the intrinsic function you need is something named compare. Also, you can search this page with comp CMP. And if you now compare the packed single precision floating point number, for example, you can search for comp PS and you find something like this. And from this list, okay, so you can figure out that probably, yeah, this MM512 comp PS mask may be what you need. So especially because it takes two values which are supposed to be compared. And this is the third argument specifies, yeah, what kind of comparisons you want to make. And you just click on this one and reveal the description. So this way you can figure out this function is what you need. Well, it is indeed what you need in this particular case. And the other thing is, so you might wonder if there is a vectorized square root instruction. So just search for this page and search this page for square root, and you can find, yeah, functions that have square root in their name. So you can hope that there will be some square root instructions, vectorized square root instructions. So in this particular case, what you actually need is, well, so there is actually a R square root, which is reciprocal of square root. So probably you want to narrow the search by saying underscore square root, for example, square root PS. Then, yeah, you get, well, it's almost exactly what you need. Like, well, this is 128-bit version. And this is 512-bit version of square root. And you can also know that, well, there's even predicated square root instructions indeed. So this way you can master the manual vectorization. Okay, so I got a question. So maybe you want to calculate in a polar coordinate system. Yeah, this is one way you can, you can do exactly the same thing. So this way you can avoid this if statement inside the loop. Yeah, so certainly this is one way you can do that. But well, here, so as a matter of practice, I still recommend you to do in the original way. And whether this integration using polar coordinate is indeed more efficient, I don't really know. But anyway, so you can do either way. So the other problem is actually more challenging. This problem 2 is about the vectorized version of binary search. So you know how binary search works. So it is a method to search for a particular value in a sorted array. So if you don't know how it works, you can just Google for whatever page describing the binary search. So here is a Wikipedia page. So this is, so basically binary search narrows the search range by half each time you make a comparison. For example, this figure illustrates the situation in which from this sorted array, you want to find the value 7. And initially, you only know that the 7 is somewhere in this entire array. So the original search range is the entire array. And you get the middle element, which happens to be 14 in this case, and compare this 14 with 7. And 7 is smaller than 14. So you narrow the search space into the left half of the original array. So you simply continue this halving the search space until it becomes a singleton. And at that point, you can know whether you find the value or there's no such value in the array. So this search for a single element is very sequential. So there is almost no way you can parallelize a single value search. But you can imagine that you want to search for many elements, and you can either parallelize or vectorize searching for many elements, right? So this is exactly what you are asked to do in this next exercise, next problem in the exercise. Where's the page? Where is the page? I don't know where it goes. Is it this? Oh, maybe. I need to go back. Okay, I don't want to bother to. Yeah, this one. Okay. So the serial binary search program is actually given, and you are asked to convert this function into a vectorized version, which takes many integer values you want to search for, right? So originally it takes only a single integer value, but you are asked to write a version that takes a vector of integers, and you return whether each element was found and where. And the main challenge is, obviously this while loop. So you wanna change this while loop into an equivalent vectorized loop that processes many elements at the same time. So all these, for example, the comparisons become generating the mask. And but depending on whether the middle value is smaller than the value you are looking for, well, you do different things, right? So you need to have a vectorized version of this if statement, right? So it's very challenging, you know. So if you're the first time you are exposed to SIMD programming, I have to say this is indeed very challenging. And even if you master the concept, the code easily ends up being very ugly. So very soon, I think you realize that you don't want to do that. So actually, I gave you some pieces of code that help you vectorize this code without making it so ugly. And this, the piece of code is given in another file here. So it has so many C++ overloading, so operator overloading stuff. So for example, by simply saying A equal B, then it generates a mask, right? So, well, I'm actually hoping that the future compilers have supported built-in, so without writing anything like this. But for now, you need to write your own small pieces of code. So like equal, yes, less than, or these kind of things. So with the help of this operator overloading stuff, where you can actually vectorize this code without making it so ugly. So this is what you are asked to do. So with that said, probably it's not a good idea to spend too much time during the class time to work on this. So I encourage you guys to take some time to do it by yourself in your home. Okay. So with that, I think I want to go ahead with the next topic, which is about how to get nearly peak flops with CPU. So what it is really about. So well, the actual concept you want to learn is actually something called instruction level parallelism. But the reason why I gave this a little bit cute title is, so with what you have already learned and what you are going to learn in this particular segment, you can actually get very close to the peak performance of the CPU. Okay, so here's the introduction. So far you have learned how to do multi-core programming, so which is very basic of OpenMP stuff. SIMD instructions. So with multi-cores and SIMD instructions, can you get the maximum performance of the CPU? This is the question. And actually, the answer was it in a way depends, but most often, but the answer is no. So you need to learn one more piece. So the last key element, important element you want to learn is something called instruction level parallelism of superscalar or out of order processors. So this is what this segment is about. But just to better motivate you, let me frame that talk in as an endeavor to get nearly peak flops, floating point operations per second on CPU. So for that, so for what I'm going to show, and it is almost exactly the same as what we did before on GPUs, which is just to write this kind of simple code doing almost nothing other than X plus B, so FMA. So it simply repeats FMA many times and measure how fast we can iterate the we can iterate this loop. So how fast you can do this X equal to X plus B so many times. So you already know SIMD, and without SIMD, you have no chance that you can get close to peak performance. So this loop is already vectorized. So a single X plus C performs L FMAs. So L is the number of lanes. And you repeat this n times. So you perform L multiplied by n FMAs. And almost nothing else, right? So how fast it can go? So do you remember you already witnessed something similar, analogous in the GPU setting, right? So let me just do it in front of you. So this is actually given in the next notebook, but so you can play with it with this later by yourself. But so that the code I'm actually giving is okay. Let me just start with setting things up, which I have already done, I believe. But okay, this is the code. Almost doing exactly what the slide says it does. So and you remember we did almost exactly the same thing on GPUs. So essentially, it does this X equal X plus B many times, or more specifically n multiplied by m times. The reason why this is written as a doubly nested loop is not very important. So I'm simply looking at the clock, processor clock from time to time. So every m iterations, right? And measure how much time that it takes. So just compile it with LLVM, and here's the output. So it executes X plus B 100 million times, right? So 100 multiplied by million. And every million iterations, I take the clock and record them. So there's in total 100 numbers taken here and recorded, right? And here's the visualization. Well, this is almost exactly the same as we used before for GPU experiment. And again, we execute it, but this time the record the result into a file. And finally, we visualize it. And you can see, yeah, how many clocks it took. So essentially how many time it took or just in terms of the processor's clocks, right? So it took 3.0 10 to 8, so 100 million. So 300 million cycles for 100 million X plus B. So it means that it took approximately 3 cycles, something like 3 cycles, to perform a single X plus B, right? So this is where our whole story got started. So this iteration runs something like 3 clocks per iteration, right? Okay, so I didn't show it, but you can look into the assembly code generated by LLVM. All right, I think I can do that just for the sake of I don't know, just for the sake of transparency. So just make another cell, copy this, and well, instead of the executable, it generates assembly code. And you get, you should get this no SIMD, no ILP.s or somewhere the left pane. So no SIMD, no ILP.s. Yeah, this is what is just generated. I just open it. And well, it's a bit challenging to locate the assembly code corresponding to the loop we are looking at, which is this loop. But you can actually locate the assembly code by searching for this string. So begin loop. So this is how you can easily locate the assembly code corresponding to the piece of code you are interested in. And down here you can, what's something a bit strange. So let me get, yeah, this is it, right? So this seems the assembly code corresponding to this x equal x plus b loop. Yeah, for one thing, it is exactly doing what I expect it to do. So it does a lot of FMRD instructions. And actually, these, well, you see 8 FMRD instructions somehow, even though there's only one x plus b in the iteration. But this is because the LLVM compiler was actually trying to optimize it. So rather than doing comparison conditional branch every time you execute this single FMRD instruction, it unloads the loop 8 times. So you do this conditional branch instruction only once every 8 FMRD. So it's pretty optimized. And okay, so this is what you exactly witnessed, right? So the question we are going to deal with is, so why does this particular loop take something like 3 point something cycles to do a single FMR instruction? Okay, so maybe you don't know why I'm asking this question. You may think why it may be what it is, but the main reason why we have to wonder why we have to think about it is when at least in the processor spec, where it says this processor or something called the Ice Lake microarchitecture, each core can execute up to 2 FMRD instructions every cycle. Yeah, this is the thing I already talked about several times, that the peak performance is attained when the processor executes 2 FMRD instructions every single cycle. But yet, what we have just witnessed is that it can execute only a FMRD instruction every 3 or so cycles, right? So this is very different from for this peak performance. So the thing is, okay, so even if the processor says it is able to execute 2 FMR or whatever instructions every single cycle, it does not mean, okay, so the processor is able to execute these 2 instructions in the same cycle and these 2 instructions in the same cycle. So in other words, it does not necessarily mean, so this peak performance, 2 FMRD instructions every single cycle, does not necessarily mean that the result of this FMRD instruction, for example, line 2, becomes immediately available to the next instruction. So this is the important concept you need to remember. So what you need to know is, so when the processor says, okay, so it is able to execute 2 FMRD instructions every cycle, it refers to something called the throughput. But each instruction has another limitation, or the performance characteristics, something called a latency. The latency is the time until the time until the result becomes available from the point that this particular instruction gets its operand input. So the latency can be, well, you can easily know the latency of many of these instructions. Well, again, by looking at the intrinsics, right, for example. But ultimately, it is specified in the processor's microarchitecture spec or manual. So you don't often see these numbers by yourself. But this is in any way. So this is what the processor actually says about the latency and throughput about these instructions. For example, okay, so these are microarchitecture names of recent Intel processors. The hardware is already somewhat old, and the relatively recent one is something called Skylake. And actually, I forgot to write another column for the processor we are playing with, which is Ice Lake. But actually, the numbers are the same as Skylake. So this 4 is the latency for floating point addition instruction. And the multiply add instructions we are just looking at has the same latency, which is 4 cycles. And the number after the slash is throughput, which is the maximum number of instructions the processor may be able to execute in a single cycle. right? So the processor clearly says, okay, so this FMR instruction has a latency of 4 cycles. You can actually confirm this by, again, by looking at this intrinsic slide, for example, FM at PS, for example, and you can open this MM512 FM at PS. So this is the most basic FMR instructions for single precision floating point numbers. And it says the latency is 4 for all the models. But there must be a law about the Ice Lake, but probably it is the same as Sky Lake. This is what this page should be read. And throughput, it's a bit confusing, but this throughput is actually something called reciprocal throughput. So you take the inverse of this 0.5, and which is 2, and 2 is the number of instructions the processor can execute. The number of this FMR instructions the processor is able to execute in a single cycle. So for all the instructions, it talks about latency and throughput. And this is determined by the microarchitecture design of the processor. So actually, this 4 is what we have just witnessed. Well, it was actually something slightly larger than 3, so it was not exactly 4. I'll get to that later. But the reason why the loop I was talking about does not run, for example, 2 iterations per cycle is this latency. Okay, so this is the piece of very valuable information resources for very detailed architectural knowledge. So you can visit this page as software optimization resources. You can jump to this page, and it has many detailed information about the many variants of Intel architectures. For example, this is the most comprehensive resources about what each generation of Intel processors is capable of. For example, it is able to execute up to 2 FMR instructions at a time. And essentially the same information is compactly summarized in this large Excel table. I don't know whether you want to look into it, but when it becomes necessary, it is very useful piece of information. So these are various microarchitectures of Intel, and for example, the end, for example, you can see it's very wide. The latest one is on the right. I don't know how to scroll this. Well, I have to do this. Okay, so this becomes fairly recent. And Sky Lake. And finally, Ice Lake. This is the model we are playing with. And for this particular architecture, where it lists all sorts of instructions, and where it has information about the latency and reciprocal throughput. So in principle, you can know the latency and throughput of all kinds of instructions. But the same instruction, the same piece of information can be more easily found in this intrinsic space if that particular instruction is indeed found in this intrinsic space. Okay. So here's the clear explanation about why the previous loop runs only so fast. So first of all, okay, so look at this series of FMR instructions. So these FMR instructions, I don't know which variable corresponds to A and X and C, but anyway, the only thing you have to understand in this is, well, ZMM2 is the variable the result is going to be written into. So ZMM2 corresponds to this variable X. And in the very next instruction, with the same value, the value you have just written into ZMM2 is immediately used by the next instruction. Okay, so this is the first observation. So FMR instruction uses the result of the immediately preceding FMR instruction. So this one uses the result generated by this instruction, and this one uses the result generated by this instruction, right? So in other words, there are something called the dependencies between them. So this instruction depends on the previous instruction, and this instruction depends on the previous instruction. Yeah, this is what this instruction sequence dictates in a way, so that the processor has to respect this dependency. Well, actually, it is obvious from the source code too. So you don't have to look into the actual generated assembly code just to understand that the next AX plus C depends on the result that comes from the very previous iteration, right? So that each iteration writes into X, and the same X is used by the immediately next iteration, right? So actually, you don't have to look into the assembly code at all just to understand there are dependencies between two consecutive X plus B operations. And remember that I have just said this FMR instruction has a latency of 4 clocks. So it means that the entire loop progresses only as fast as 4 clocks per iteration. So this is the one FMR instruction executed, but the result becomes available only after only 4 cycles after this instruction gets executed. So the next instruction is just waiting for the result from the previous FMR to become available. So that is the reason why it takes 4 cycles per iteration. But you may say, wait, it was not 4 instructions exactly. It was something like 3 point something cycles, right? So sorry. So it was not exactly 4 cycles you observed. So the reason why it was not exactly 4, but instead it was something like 3 plus something, was actually there are 2 kinds of clocks in the processor. So probably you may have something like this. So recent CPUs change clock frequency dynamically depending on the load. So while you are doing almost nothing, well, just using, for example, PowerPoint or browsing the web and just thinking in front of computers. Computers are not doing almost anything. And in these times, the CPU tries to save the energy by lowering the clock frequency. Right. The clock we have just measured in the program we were talking about is actually something else. So it is called something like a reference clock, and this reference clock runs at the constant frequency, no matter how much the computation the CPU is carrying out. So in the illustration, there are two kinds of clocks. There are two kinds of frequencies. So one is the clock called a reference clock that ticks at exactly the constant rate, but exactly precisely proportional to the absolute time. So So it was this reference clock we were measuring in the program we are talking about. So we are, in other words, we are measuring the exact absolute time. On the other hand, this CPU clock or something called the core clock, well, varies over time. Well, sometimes it runs faster, sometimes it runs slower than a reference clock. So if the processor happens, the core clock happens to be faster than the reference clock, then you get something like 3 clocks, right? So 3 reference clocks to be precise. But internally, it was actually still the exactly 4 core clocks. So when you actually measure the execution time in terms of core clocks, you get exactly 4 clocks. So this is actually the matter of how you measure the performance. Well, actually, you can actually witness the single iteration takes exactly 4 core clocks by just changing how you measure the execution time. So this is it is what. Okay, it does after this SIMD section. So it is almost exactly the same thing, except that this time we are using SIMD instruction. And when you execute and visualize it, well, you get, again, something like 3 clocks per iteration, right? And well, I'm making the same note in the Jupyter notebook too. So there are 2 kinds of clocks. And this section is about measuring the time in terms of the core cycles, and omitting the details. So you wanna look into the code later by yourself, but by changing how you measure the time, so this time you get almost exactly 4 clocks per iteration. So it is exactly saying the number of core cycles per iteration is 4.0015, something like that. So it is actually very instructive to actually witness that the number of cycles a single iteration takes is almost exactly the integer, right? So there's no, for example, 3.5 core clocks for executing a single iteration. Which is just as a matter of getting more confidence about your understanding. Well, it is actually useful to witness something like this. So the number of cycles per iteration is almost an integer, right? Then, okay, so now you understand the main thing. And what we are going to talk about is, okay, so when you do something like what I have just shown, well, you can never run faster than 4 core clocks per iteration, right? But how you can actually get more performance? and how you can actually get close to peak performance. So this is exactly the next what the next section is about. So after understanding the performance is limited by this latency, well, how you get actually beyond that. So how to overcome these latencies. And the answer is actually very simple. Just increase the parallelism and no other ways. The important thing you have to know is that, well, there is no way that, so even if you, desperately asks to ask the processor, I wanna make this loop run faster. But as long as if you have only a single x equal x plus b, there's no way you can run this particular loop faster than 4 cycles per iteration. The only way you can increase the overall performance, not the time to execute this particular loop I was talking about, is to increase parallelism. So like I said, you cannot make a serial chain of dependent instruction whose execution time is dominated and determined by the latency. So, like I have just explained, if this instruction takes the input from this instruction, and if this instruction takes the input from this instruction, then you cannot run this chain of dependencies run faster than 4 cycles per iteration, per back-to-back FMAT operations. The only thing you can do to increase the overall performance is to increase throughput. So in other words, you simply do other things, right? So other things, I mean, some other computation that do not depend on the first chain of computations we have just talked about. So if you do this, then the processor might be able to execute these 2 instructions in a single cycle, because there are no dependencies between them. So to be more concrete, to be more specific, if you write something like this, so almost exactly the same loop as before, but you have 2 similar statements, x plus b, but on different variables, which is the very important part. Then something like this may happen. And the net result you are going to observe is that the entire execution time does not increase at all, even if you double the total number of flops you are performing. And this is how you can actually get the close to peak performance. So, okay, so just to continue this direction. So instead of updating just a single variable, whose operations necessarily depend on each other, you just have independent chain of computations. And you increase the number of independent computations until you get something close to the peak. So in this specific example, so in a single iteration, you update NV number of different variables like this. Well, just imagine you have NV different statement like this. Well, I'm just writing it in terms of the loop. So what we expect is if this NV becomes larger than 8, then if a single FMR has a latency of 4, if you have 8 or more of them, then in each cycle, it executes 2 FMR operations, FMR instructions, every single cycle, and this continues. So this is how you can get a peak performance. So the important thing is you cannot make a single dependent chain of computations any faster than what the latency dictates. The only thing you can do to increase the performance is to do many of them. Well, in other words, increase parallelism. In a way, the situation is conceptually very similar to what you have witnessed on the GPU, right? So on the GPUs too, well, so when you have only a single thread, well, it was kind of slow, right? But the thing is, okay, so you have many of these threads doing almost exactly the same thing. That the execution time almost never increases until you get many, many threads, right? So it is all about parallelism. And this is how processors actually get good performance. So the point is it's not able to execute this kind of serial chain of computations surprisingly faster. And this is a simple experiment you are going to do by yourself in the Jupyter notebook. But this is the actual result showing what happens when you increase the number of variables. In other words, this NV from 1 to a very large value like 16. So this is the number of cycles a single iteration takes. So the remarkable thing is, so you increase the number of variables, thereby increasing the amount of work you are doing in a single iteration. But the execution time doesn't increase at all up to some point. In other words, the throughput, the number of FMR operations per the unit amount of time, almost linearly increases up to some point. And at some point, it reaches the peak performance of the processor, which is determined by the number of execution units that the processor has. So you cannot indefinitely increase the number of variables and get the proportional performance gain. Well, of course, there's a natural limit that stems from the resources the processor has. But the things are sort of very simple. And this is another thing you can actually witness by yourself in this Jupyter notebook, in this section of SIMD multiplied by ILP. I guess I think it's time to finish for today. But well, so I don't know how surprising all these things are to you, but well, you're actually learning a very important concept. The other thing I want you guys to take away is, well, getting close to peak performance for whatever processors, GPUs or CPUs, it is not always easy, but conceptually it is that easy. So if you increase the number of variables up to something like 8 in this particular example, then you can actually get close to peak performance. And accomplishing this kind of performance for something more realistic and useful is of course another thing. And you're going to do some exercise around this topic, well, especially for matrix multiplication. It's going to be your next exercise. And finally, I got a question. So how to reach peak performance? Keep parallelize more until you can get a better result. Is that correct? Well, so just for the purpose of demonstrating, yeah, under what kind of situation the processor is able to get peak performance. Yeah, I think you are just about right. Of course, in reality, you are given the problems you need to solve first, and you cannot change you cannot change what you do just because you want to get more performance. So the thing is actually more complicated in reality. But just for the matter of understanding when you get close to peak performance, I think you got the point. Okay, is there any other question? Did I answer to your question? I think I hope so. Okay, so could I upload lecture recordings today on YouTube? I'd like to use them for review. Okay, so I guess you want to see the YouTube video today, right? So I'll do that. Okay. So I think that's it for today. So see you next week.